With the class. So in the previous class, I think the recording has started, right? Yeah. Right. So in the previous class on Monday, we looked at how do we design a common emitter amplifier. Basically, we are in the process of designing an amplifier. And how do we go about designing a common emitter amplifier? We derived the gain expression. We looked at it from a more intuitive angle. And we also looked at it from the small signal analysis, and we saw that both of them are pretty much the same. And I raised a few questions towards the end of the class. Okay. Now, before I go and answer, I said that we will be looking at the solutions to those problems by using appropriate circuit techniques. But before we even do that, I want to look at it a little more from a practical angle. Okay? Let's say we have an ideal amplifier, which is expected to have, let's say, a gain A. Right? Now, if you recall, at the very beginning of our class, we said that it has a source with a source impedance, right? And it was also going to have a load impedance. RL, right? Now, this is how your amplifier is going to be, right? And we said that this amplifier is going to have some input impedance, and this can be thought of, a voltage amplifier can be thought of as A times V in with a certain output impedance driving this load RL, right? Correct. So I hope you remember this, what we did in the right at the beginning of this course. Now, if you take this common emitter amplifier, right? Now, we said this is our RC, this is our VCC, this is our transistor. Now, we have our source, let's call this as VS. We have our RS, right? And in the previous class on Monday, I said that this signal has to ride on top of a DC, and the way we bias it is that we are going to use a resistive divider to bias this whole thing, and we will use a DC block capacitor, let's call it C1, to make sure that the DC does not go back to the sensor or your source, because the source can drain all your DC current. So if you don't have this, right, you can have a DC current path like this, right? And the DC current sometimes can damage your sensor also. And even if it does not damage your sensor, you are unnecessarily wasting current by pumping it into a sensor which does not need it, right? So, and also it may even happen that the sensor by itself might need some different DC point, okay? And it can also happen that whatever we model as VS and RS can very well be a previous stage of amplification. There can be an amplifier which is driving the next stage of an amplifier, right? You can have two amplifiers in series, cascaded amplifiers, right? So you don't want your DC to go and mess up somebody else's DC. Neither do you want their DC to come and mess up your DC, right? So in order to do that, you put a DC block capacitor to make sure that you are biased at the right point, okay? Now, how do we connect the load? Can you tell me? I have my load resistor, RL. Now, how do I connect my load? Can I directly connect it here? Is this okay?
Capacitor is used.
With a capacitor.
Yeah, okay. Why should we use a capacitor?
To get AC output.
Okay, correct. But suppose I don't use a capacitor and put it like this. What do you think will go wrong?
So it can affect biasing.
It can affect the biasing. So how will it affect the biasing? You're right, because the current that is flowing through RC will now get split into two parts, one through the transistor and the other through the load resistor. Now, because of you would have designed this, if you don't put the DC block, now let's say you will never know if you are designing an amplifier, you will never know what kind of a load is going to be connected. For example, let's say you are designing an audio amplifier. You don't know what kind of load is going to get connected. Okay. Right. So I'm just giving you an example, but typically, I mean, this will typically not be at the final stage of your audio amplifier, but you don't know what is going to be there. The RL can change, right? From application to application, your RL can change, right? So what will happen depending on the RL, the voltage across this RC can change, and it can even push this transistor into the saturation region, right? Now the same way, if you take common source amplifier, and if you put another RL, now because there is too much drop across RD, it can push this MOSFET out of saturation region. It can go into the triode region, right? So you don't want this kind of a behavior, and therefore you don't want DC current to unnecessarily flow. You are looking at an AC signal which is coming in, and that AC signal should get sufficiently amplified, right? So you have to put another DC block capacitor. Is it clear why we use a DC block capacitor even at the output? Because if you don't do, this load is also going to draw some DC current from the supply, which is not needed because you are only interested in the AC signal here, right? And that extra current is going to flow through RC, right? And you basically have a KVL here, so some amount of current here, some amount of current there, and it's going to mess up your DC biasing. All right. Okay. Now, this is how we are going to connect your transistor. Okay. Now we looked at the R in of this particular amplifier, and we said that this was going to be what? You have R pi being the input impedance of your common emitter in parallel with R1 parallel to R2. Okay. We saw this in last class. Now, what is the output impedance? We didn't see the output impedance, right? So for output impedance also, what you will do is you draw the small signal equivalent circuit. I'm just interchangeably using VBE and R pi and all that, right? You have RC, right? Now the capacitors become a short, okay? All the capacitors become a short when you draw a small signal equivalent circuit, at least the low frequency small signal equivalent circuit, right? Okay. Now you want to know what is the output impedance looking at this particular place, right? Let's say this is your base terminal, collector terminal, emitter terminal. This is your thing, and then of course you have R1 parallel to R2, and then you have your this one. So while finding the output impedance, what you will do is you go and set V in to be 0. Okay, so this whole part is, this V in is set to be 0. Okay, so which means that VBE is 0. Correct? And what will you do? You set up a test voltage source at the node at which you want to connect and measure the current. So I'm going to put a test voltage source, and I want to measure what is the test current. Right? Correct? This is what we need to do. Okay. Now VB you have set it to be 0, and therefore, anyway, the left hand side, this whole portion doesn't come into the picture at all. VB is 0, and therefore what are you left with? You are left with only R0 and RC. Okay, with VT and IT. Therefore, your R out is equal to what? R0 parallel to RC, which can be approximated to be RC. Okay. Is this clear? Any doubts? Any questions? When
Sir,
you're
what
calculating,
exactly
yeah.
is R out?
Sorry?
Sir, what exactly is R out?
Okay, let me go back to this one. So here you have an R out, right?
Okay, so that's the resistance seen from the output side. Sir, but then
Output
what
side.
about RL? Why are we ignoring that in the second circuit?
Yeah, because this is your amplifier. No, I am looking only at this amplifier. Okay. Okay, it is, you have an amplifier, it is driven by a source and it drives a certain load. Okay. This is your amplifier, this is your load, and this is your source. Fine. Now I am interested because let's say you're building an amplifier and you're going to sell it. You have to write your data sheet, right? In the data sheet, you have to provide what is the value of the input impedance, what is the value of the intrinsic gain, and what is the value of your output impedance, right? Now, how will you determine the output impedance of this particular amplifier that you have designed? Okay, that is what we are talking about. Okay, this is similar to your, Thevenin equivalent circuit that you would have said, right? Like you would have studied. So you will measure what is the voltage and the impedance. How will you measure? You basically put a test voltage source and see what is the current drawn and what is the impedance, right? That is what we are doing here. Okay. If you want to measure the input impedance, you put the test voltage source there, measure the current, take the ratio, that's your input impedance. All right. So if you, in this particular amplifier, we have seen that your Rin is going to be R1 parallel to R2 parallel to R pi. My gain is going to be given by the intrinsic gain of the amplifier. Gain of the amplifier is given by what? GM times RC. The more exact expression is R0 parallel to RC. The minus. It can be approximated as minus GM times RC. The output impedance is given by R0 parallel to RC, which can be approximated to be RC. Now, what is defined as the overall gain is when you have this full structure, right? The overall gain is for this entire structure which I have drawn here. You have Vs, you have Rs, you have R1, this is going to be your amplifier. Let's say the amplifier starts with this is going to be your amplifier, right? And you have a certain RL. Now, how can we write the overall gain? Can you tell me? Or let's say, first let us write the overall output. The actual V out can be written as what? First of all, Vs into Rin divided by Rin plus Rs multiplied by the intrinsic gain, which is minus Gm times Rc, correct? And this, of course, has to be, there is an output between, you have the RL divided by RL by RL plus R out. Now, what will this result in? You have Vs Rn divided by Rn plus Rs into minus Gm Rc. This is nothing but Rc, right? You have RL divided by RL plus Rc, correct? Now, if you combine these two terms, what will you get? Vs Rn minus Gm divided by Rn plus Rs. This can be written as Rc parallel to RL, correct? You have RC divided by RL plus RC, which is nothing but the parallel combination of RL plus RL and RC. Right? Now, this you can also use in the overall. So this becomes your overall expression. So your Hey guys, are you able to hear me?
Yes, sir.
Yes, sir.
Okay, I had some weird internet issues here. So I don't know up to what point you could hear me and where it got disconnected. Let me share my screen once again and please help me out with that. So up to which point were you guys able to hear me?
Last slide before this. Yes,
Okay,
sir. Sir,
yeah.
sir, can you explain how you get the expression for R out Vs R in by R in plus Rs minus GMRC?
Oh, this V out.
Yes, sir.
Okay, yeah, I'll explain that. So if you look at this particular thing, so this is, let's go to this one, right? Now here, if this is your V out, how will you write V out? V out can be written as, A times V in multiplied by RL divided by R out plus RL, correct?
Yes, sir.
Now what is your V in? V in can be written as Vs into Rn divided by Rn plus Rs. So put both together
Yes.
and you'll get. So here the gain which I have used is minus GMRC. That's it. Okay. So you have Vs
And
times Rn divided by Rn plus Rs. That's the actual input coming into your amplifier multiplied by the intrinsic gain of your amplifier and then RL divided by RL plus R out. Now here R out is approximately RC. So I'm using this to get this expression. Is it clear?
yes, sir. And sir, this intrinsic gain is only for the amplifier. The
Yes.
overall gain for the whole circuit will be different.
Yes, overall gain I'm defined. So the intrinsic gain is basically, so let me just draw this. So this is Vs, this is Rs, right? Let's say C1, C2, R1, R2. Okay. Now this can be expressed basically. I'm comparing this with an a black box of an amplifier, right? All right. So in that case, my A is going to be, this is my amplifier. All right. So the intrinsic amplifier is this much. The overall gain is defined as V out divided by Vs, and I'm defining this node voltage as Vn, whatever is occurring here. All right. Is it clear? So intrinsic
Yes.
gain we saw here. The overall gain is what I'm writing here. So this is the overall V out expression, right? This whole term can be taken as RC parallel to RL, and therefore, if you write the overall gain defined as V out divided by Vs, okay, it is given as minus Gm RL parallel to RC multiplied by Rn divided by Rn plus Rs. Of course, you can expand Rn, which I have not done to make the, just keep the expression more clutter free. All right. But this is your overall gain. Okay. So is it clear? Any doubts in this aspects?
So could you just go to the previous slide for a second?
Yeah.
So, yes, sir, that's it. Thank you, sir.
Okay. All right. Okay. So now that we have seen how you can build an amplifier, a simple common emitter amplifier, and then kind of, relate it to the ideal notion of an amplifier, or rather the block level notion of an amplifier, where you take this common emitter amplifier and define its input impedance, the output impedance, and the intrinsic gain, and of course the overall gain in terms of the full system. So that is what we have seen so far. Now, let me repeat the questions that I had. The first one is, what happens when beta varies? Secondly, what happens when temperature changes. All right. Now, so far we said that this value at this particular node is biased at, let's say, such a VBE. Okay, the whole point of the biasing thing is such that the capital VBE is such that it gives you a certain capital IC, which results in a certain GM, which results in a certain gain. Correct? This is the flow of thought. Or rather, when you're designing, if you want a certain gain, you say, okay, I need a certain GM, and you say, okay, to get this GM, I need a certain collector current, and therefore I will need to give this VBE to be a certain value such that it is going to make sure that IC is constant. Now, we all know that if you put a certain VBE like this using this resistive divider, there are other issues with it, we will go into it. Now, if temperature changes, what happens? And if beta changes, beta will definitely change, because even in your lab, if you were to do an in-person lab, you will have, each of you will get a transistor, or rather every group will get a transistor, a group of 3, and you will measure the transistor in the multimeter and say, okay, the HFE is so much. So one person will get 250, another person will get 190, one person will get 220, something like that. Okay. Now, how do you design a circuit which is going to be robust enough such that, despite this variation of beta, despite the variation of temperature, my gain remains fairly constant. So, which means that we need a mechanism such that VBE is adjusted automatically based on IC. Or rather, as temperature increases and collector current increases, you need some mechanism by which you reduce your VB. And when your beta is different from one board to another board, let's say one beta is lower and therefore you get a little lower collector current, you have to go and increase your VBE such that you get the same amount of IC. Right? So you need a mechanism which will look at the amount of current that is being drawn, look at IC, and then go and tweak your VBE. And this process has to happen continuously, and this process has to happen automatically. Right? You cannot have a potentiometer and then you look at an ammeter, go and change it, and then after 2 minutes you look at the ammeter, go and change it. That is not, you cannot do it manually. It has to happen automatically. Now, how to do that? Okay, one very elegant solution. Okay, although it looks like a very complex problem, a very elegant solution is basically to introduce one resistor at the emitter like this. Okay. So now, for the time being, let us forget about all the other things around the amplifier. We will only be concerned about okay, or let me even get rid of this stuff. Okay, let me now say I have a VB here. Okay, now let us say I give a fixed VB. Let's say I am going to generate the VB through a resistive divider, whatever. Okay, now let's say in one case the beta is changing or temperature is changing. Let's just take the example, the first case where let us say the IC increases a little bit. Maybe the temperature has changed, or maybe it's another design where you have a higher beta. Whatever it is, your IC has increased. Now, since IC has increased, what will happen? It basically means that the emitter current also has increased, because IC is almost equal to I for all practical purposes. So, which means what happens to this emitter voltage?
Increase.
Yeah. So this will lead to VE increasing. Now, if VE increases, what happens to your VBE, the base emitter voltage? This will decrease.
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 All right. Okay, let's take the inverse case. Let's say for some reason my collector current is less, which means that my emitter current is also less, right? Maybe the temperature has changed, or maybe let's say you are using it in a board where the beta of the transistor is lower. Now what will happen to the emitter voltage?
Decrease.
Emitter voltage will decrease. Correspondingly, my VBE is going to increase. Now, what do you see here? You have some automatic mechanism whereby you're kind of correcting, right? Now, yes, it is not going to be a very perfect correction, but what you have done is that you have taken a device whose collector current is going to vary very widely, and instead of that, you are going to have a much more tighter variation. Okay. Now, this is what is called as negative feedback. I think, have you guys studied about feedback? Not yet, right? So you'll anyway look at feedback. We will look at feedback even in the analog electronics course. You will look at negative feedback in a much more detailed way in control systems course. I think control systems is in your next semester, I believe. So, all those things are there. So, but this is a very classic example of negative feedback. Okay, that is to say that if some quantity changes in one way, the circuit or the system works in such a way that it brings back to the original quantity. All right. Now, this is what we are going to use, and this is what we are going to use to stabilize our bias. If you do not use this, you might just put some, biasing condition, but at the end of the day, what you will get is pretty bad. All right. So this VBE, this is the way by which you stabilize your bias across component variation, that is BJT component variation, and you also stabilize your design across temperature variation. Any doubts, any questions?
Sir,
Yeah.
sir, then in this case, how do we resolve the issue of tolerance of R1 and R2?
Tolerance is an issue. Tolerance will be an issue. So basically what will happen, yes, let's go to, that's a good question. So you're going to generate this by now it is not only the tolerance of R1 and R2, it's also the tolerance of RE. Okay. So the way, first of all, how will you, so at the end of the day, what will happen is that you will get a certain VB here. You will nominally have around 0.7 volt here, right? And you'll have the rest here, VB minus 0.7 here. Okay, this is a very quick hand calculation. This works out, at least to a first order, it will work out fine. Okay, so basically your current is set by, your emitter current is pretty much set by VB minus 0.7 divided by RE. All right. So the most important thing is, as you pointed out, R1, R2 variation will be there, RE variation will also be there, but the tolerances will, so for example, if you expected 1 milliamp, you will probably end up with plus or minus 10%, which is still okay. All right. If you didn't have that, if you allowed the BJT to do whatever it wanted to do, then you'll have a much worse variation. All right. Does it answer your question?
Yes, sir.
Yeah. Okay. So if when you try to design the circuit, if you want to design it for a certain current, this is the way you do. You know that the collector current, emitter current is given by VB minus 0.7 divided by RE. We can safely, this is an approximation. Okay. So I have had this comment in the past from some students who say, okay, you're using too many approximations and I'm not comfortable with that. But if you step into the world of actual engineering design, there is quite a bit of approximation involved. Okay. You cannot sit and write an exponential function here and try to solve equations. This is what is called as back of the envelope calculation or back of the envelope design. That is, you make a lot of assumptions. Here there is one more assumption which I have not yet pointed out, which is that IB is here. Okay. So now this IB has to come through R1, which means that this VB potential will not be equal to actually R2 by R1 plus R2. Okay. So that issue is also there. Okay. So these are all there, but then the deviations are a little smaller. Okay. So if you design it for 1 milliamp, you'll at least see either 1.05 milliamp or 950 microamp or something like that, plus or minus 5-10% you will see easily. Okay, but that is still acceptable than something which is completely uncontrolled, like allowing the BJT to run freely. Okay, is it clear? Okay, now let us build the whole amplifier around this thing. So what else do? We put a capacitor RS. Now you have your RL. Okay. Now you tell me, without even going into the mathematics of it, we have included one more resistor. Do you think that the gain will remain the same? Whether it will increase, decrease, we will look at it later. But you tell me whether the gain will remain the same.
Sir?
Yeah.
Sir, in the previous where you had written what happens when beta varies, that IC increases, IE increases. Sir, I did not understand if VBE decreases, then sir, how is IC also decreasing?
Yeah, VBE decreases, IC will decrease, right? See, let's say the temperature has gone up for some reason. Okay, ambient temperature plus also junction heating, junction temperature, something, right? So if you initially, let's say I mean, this is like, okay, how fast the system reacts and all. Let's just say this whole system reacts within a few hundreds of nanosecond, or let's say microsecond. Okay. So when you still have that larger same amount of VBE, it results in an increased current, right? Now that increased current immediately produces an increased voltage, which goes and reduces your VBE such that the current is brought back.
Yes, sir.
Understood. This
Yes,
whole
sir.
process will happen within, maybe a few tens of nanosecond, or maybe depending on the capacitances that are there, it will happen according to that speed. But other than that, it will happen quite fast. You really cannot capture it so easily on an oscilloscope and so on. But what you will see is that as things change, you will only see that, the current is pretty much constant.
Okay, sir.
Okay.
Thank you.
Sir, so this takes care of the beta effects as well as the temperature effects? Hello, sir. Sir?
Yeah.
Sir, so by putting RE, we can take care of the beta variation across transistors as well as the temperature effects in the conditions, like
Correct.
temperature conditions. So both will be sorted by RE.
Both are sorted out by RE, because ultimately what you have is collector current variation.
Okay, sir.
Okay, so now let us draw the small signal equivalent circuit. Okay, so how will you draw the small signal equivalent circuit? Let's start with the transistor by itself. This is R pi, GM VBE, this is VBE, right? You have R naught. And then now here you cannot go and ground the emitter, because the emitter is not grounded. Emitter has a resistor to ground, right? So you have to put RE here, and you have this. The collector resistor RC is from collector node to ground, right? So you have RC like this. Same way you have R1 parallel to R2 like this. Correct. This is your, let's say this is your VN. First we will find out what is the intrinsic gain, and then we will do the rest of the stuff. Okay. Now R1 parallel to R2 is directly in parallel with Vn, so that really doesn't do anything. Okay. Now let's say this is VE. Okay. Now what is your V out? V out is basically going to be, okay, the RC is directly there. You can kind of assume R0 is much higher. Okay. And to simplify things, for simplification, assume R0 is much greater than RC, RE, etc. and therefore neglect it. All right. So if you neglect this R0, what do you get? V out is basically going to be the current GM VBE minus GM VBE drawn through this RC. Correct. This is your output. Okay, let's hold on to it. Okay. Now what is your VBE? What is VBE? Now VBE is nothing but Vin minus this voltage VE, or rather I can write Vin to be equal to VBE plus VE. Correct? Am I right? Okay. Now my Vin should be written as, so what is my VE? VE can be written as this current IE that is flowing multiplied by RE. Someone had a comment?
So there is RS also, no?
Okay, RS we'll take care of it later. I'm right now calculating only the intrinsic gain. All right, I'm only interested right now in the intrinsic gain. Okay, which is why I have not put RS. I have not put RL also. Okay. So while calculating the intrinsic gain, we want to know what is VE. VE is nothing but the total current which is flowing through RE multiplied by RE. What is the current flowing through RE? It has two branches. One is VBE divided by R pi, that is this current, and the other current is GM VBE. Right? So let us write this. So VE, okay, yeah. So you have VBE plus VBE by R pi plus GM VBE, these two terms multiplied by RE. Okay. Now let's take this VBE as constant, not constant, I mean take it out common. So you have 1 plus R pi plus GM into RE. Correct? This is what we get. Now, if you do some simplification here, what can you write? You can write this as this, take R pi out as common. You have R pi plus 1 plus GM R pi into RE. Okay. Now, this GM R pi is what? Beta. Correct. So, this can be written as VBE by R pi multiplied by R pi plus 1 plus beta times RE. So let's keep this expression here, and we can find out what is VBE here, right? So which means that VBE can be written as Vn times R pi divided by R pi plus 1 plus beta times RE. Correct? Now let us substitute in the V out expression, which is nothing but minus GM VBE times RC. Now, what is minus GM times R pi times Vn times RC divided by, what do we have in the denominator? You have R pi plus 1 plus beta times RE. Correct? This is what you get. and this can also be kind of you can try to simplify this by removing r pi, and then okay, v in r c, and you will say okay, this is 1 plus 1 by r pi plus gm times re. Now 1 by r pi is usually quite smaller than gm, so this can be approximated. So let's say the intrinsic gain av can be written as V out divided by V in, which turns out to be minus Gm times Rc divided by 1 plus approximately Gm Re. Okay, because 1 by R pi is taken to be much smaller than Gm. Or in other words, you know that Gm R pi is much greater than 1, right? This gives us this inequality. Because GMR pi is nothing but beta, your beta is around 200, right? So which is much greater than 1. You can kind of write this approximation and say my intrinsic gain is now this. Now if you look at this expression, the numerator is your original common emitter gain, right? And the denominator is your degeneration factor. Or rather, you can think of it as you have your common emitter gain, but this is divided by the factor 1 plus gm times re. Okay. Now whatever we saw here, okay, this is what is called as a common emitter amplifier with emitter degeneration. Okay. Common emitter amplifier with emitter degeneration. In other words, what we are saying here is this emitter resistor that we have put, while it stabilizes my DC, it is resulting in a degeneration of my gain, or rather a decrease in my gain. You understood? It is doing a lot of good things, but in electronics, as in practical life, anything that does a lot of good on one hand will also have some trade-off, right, where it is going to have its own impact. And the impact here is that it is reducing your gain, and the reduction, the amount by which your gain is reduced is this factor 1 plus gm re. Is it clear? Okay. So sometimes for hand calculation, this can even be further simplified as, this is the actual expression. You can even kind of further simplify it, like if you divide gm, divide the numerator and denominator by gm, what do you get? You get a minus rc by 1 plus gm, 1 by gm plus re. It can be further, kind of crudely simplified to be almost approximately minus rc by re. Okay. In other words, if you want an intrinsic gain of 10, you have to make sure that my rc by re ratio is 10. Okay, that is to say, if you are going to use a resistor of 5 kilo ohm here and you want a gain of 10, your RE should be at least 10 times lower than that. Okay, that's a very approximate expression. The exact thing will be a little different. Okay, understood? So now this is how your gain is. So just keep in mind the gain is basically given by RC by R. Any doubts, any questions?
Hello, sir.
Yeah.
So this minus sign indicates that our wave will be out of phase in
Exactly.
gain.
Yes, yes.
Yes, sir.
So just like how we saw in the previous class, there's a 180-degree out of phase, 180-degree phase shift between the input and the output. All right. Okay. All right. So in this week's lab, I hope we will try to do a design of a common emitter amplifier with this particular thing. Now, with the with basic hand calculations, with the approximations that we have used, we can get a fairly close enough gain. Okay, so this is what we will be doing in this week's lab session. All right. So with that, I'll wind up today's class. If you have any other doubts, questions, so please go through the material in Cedra Smith. Okay, and because like these are all quite new concepts, and this might be given under the heading of common emitter amplifier with emitter degeneration. Please read through the textbook. That is quite important. In fact, there is one more hack that people do. I'll just give you the hack. All right. Suppose you say, I don't want this gain to be reduced. Okay. But I still want my bias stability. Okay. That is kind of easily achieved by putting one capacitor here. Let's call it C3. Now what will happen? For DC, it gives you DC stability, bias stability across temperature variation, transistor beta variation and so on. But but what happens for your AC signals? The capacitor acts as a short for your AC signals, and you have the gain expression for a typical common emitter amplifier for AC signals, which is GMRC minus GMRC. Okay, so this is another technique that people use. So you have DC biasing stability, but you still get the higher gain that you get from your. You kind of remove the degeneration effect for your AC signal. Okay, is it clear?
Yes.
All right. So with this, with this I'll wind up today's class. Any doubts, any questions, let me know.
Sir, so there is no option in Moodle to submit the lab report of the previous session. So can you please
I
update
forgot
that?
to add it. So let me, let me add it. Thanks for reminding. Okay, I'll add it. So how was your lab experience last week? Was it okay? Actually, I couldn't join last week because parallelly there was, I think, another 1 or 2 meetings that were going on and I had to attend. Yeah, I'm just looking at the chat. Yeah, the syllabus is still what we have covered today. Okay, so this Friday I'll try to be there for the lab session. I'll guide you through the design process. Okay. Yeah. Any doubts?
Sir?
Someone had any comment? Yeah.
Sir, can you explain the last part in which you said why we are adding C3?
Why we are adding C3? Okay. So what happens is, if you add C3, it is going to be an open for DC signals, and it's going to be a short at AC signals. You design the value of C3 in such a way. Okay. Now, when you do that, what happens? For DC, this RE is in picture, and this RE makes sure that your biasing is quite stable. Your DC bias is stable across temperature as well as beta variation. But for AC signals, what happens? This RE gets shorted out by the C3, and therefore only RC is in picture. Your RE in this expression goes to 0. Okay. Because of the effect of the capacitor. Okay, so you are left with only the common emitter gain, the typical common emitter gain. Okay, you don't have the emitter degeneration.
Okay, got it.
Right. Good.
Okay, got it. Thank you.
So in this the small signal analysis, this RE will be short because of capacitor.
Yes.
Sir, so then we, in the gain expression, we will just have minus GMRC.
Yes.
Okay, sir.
If you add this C3, so it is sometimes called as the bypass capacitor. I'll go through all that in the next class. I think Monday you have your quiz, so we may not have the class on Monday. Tuesday's class will be there. I'll go through those things. Okay.
Yes.
Right. Okay. Thanks everyone. Have a nice day.
Thank you, sir.
Thank you, sir.